Okay, for what we have, continuing on with first order linear differential equations, and we have already looked at these in the realm of where we have been able to separate the independent and dependent variables apart from each other. And we will look at some cases where the equations are not necessarily such that they can be separable. And for what we have in the case of first order linear differential equations, okay, just like a linear equation, you're looking at first order. And so for linear, okay, we're looking at first degree in the dependent variable. And again, you'll have those equations that are separable and those that are not. And there is a technique that we're going to use for this particular section, regardless of whether the equation is separable or not. And now, for what we have regarding a first order linear differential equation, okay, this will be of the form whereupon we'll say if we have y to be the dependent variable and x the independent, okay, we're going to have dy over dx plus a coefficient p of x times y is equal to q of x. Okay, and for what we have in the case of the dependent variable, okay, that is going to be y itself. So we're looking at y to the first. I've had something like the square root of y squared, y cubed, or y to the 1/5, let's say, then this would not be a first order linear differential equation. And for what we have in the case of a first order linear differential equation of this type, okay, now we're going to have a solution set up involving what is going to be referred to as the integrating factor. Okay, so we're going to have the solution set up to involve the integrating factor. And this will be whereupon we have the natural logarithmic base e is raised to the integral of p of x dx. And looking at what we have here, okay, just going back to our equation. Okay, so in terms of what you're going to do with the integrating factor, you're going to multiply all the terms in this equation all by the integrating factor, again, which we have at e to the integral p of x dx degree. Okay, so just looking at what we have now. Okay, so just multiplying all the terms out. Okay, so we're going to have, once again, we have e to the integral of p of x dx dy over dx and we have plus p of x, and see we have times e to the integral p of x dx. Okay, and we have times y. And again, q of x is also going to be multiplied by the integrating factor. And so for what we have on the left-hand side, okay, what is going to happen here is that for the left-hand side of the equation, okay, what I have here is going to be the product rule expansion, that is in the derivative case, of taking the derivative of the integrating factor times the dependent variable. So compacting this expression on the left-hand side. So the left-hand side is going to be the product rule expansion of taking the derivative in x of multiplying, once again, the integrating factor times the dependent variable, again, which we will have with y. Again, we have is equal to q of x Okay, so this is what we have thus far. Okay, now, if I integrate with respect to x on both sides, so if I integrate with respect to x on both sides now, if I integrate the left-hand side, the integral with respect to x will take care of the left-hand side. Okay, so for what we will have is that we're going to have 4 left-hand side. Okay, so I'm going to move the differential dx over. Okay, but again, first things first. Okay, so I got what was contained in the brackets and integrating with respect to x on both sides. Okay, we're going to have the integral of q of x times the integrating factor, and we'll say we have a constant added on the right hand side. Okay, so this is what we have here, and looking at expressing in terms of y itself. Okay, so I'm going to divide by the integrating factor, which in this case will be multiplying by e to the negative of the integral of p of x dx. Okay, and so looking at what we have now, okay, so we're going to have, in this case, right, so we have the integral of q of x times the integrating factor plus c, and we have times e to what is going to be the negative of the integral p of x dx. Okay, and just kind of getting things warmed up, let's say that through the use of the integrating factor, if we're looking at solving for y, and we'll say in this particular instance, okay, let's say we have dy over dx plus 2xy is equal to 0. Okay, so I already had this in the standard first order linear diffuse setup. Okay, so you got your dy over dx, and you got p of x at 2x times y, and the q of x is going to be at 0. And so if you notice, okay, we have in the setup, okay, now you got with the coefficients of the y term at 2x, again, you have a first order linear differential equation to be where we have y to be a first degree. So we now have p of x is equal to 2x. And for what we have in the case of the integrating factor, I'll just use IF for short. Integrating factor, we have e to the integral p of x dx. So we're looking at e to the integral of 2x dx, and the antiderivative of 2x is going to be x squared. Okay, so we have the integrating factor is going to be e to the x squared. So looking at multiplying all the terms in the equation by e to the x squared. So you have e to the x squared dy over dx. And we can say that we have plus 2x times e to the x squared times y is equal to 0. Okay, and for what we have in the setup, okay, now these two terms again will be the product rule expansion of taking the derivative in x of the product of e to the x squared times y. And once again, looking at what we have here, if I integrate with respect to x, okay, so we're going to have e to the x squared times y is equal to the integral of 0 dx, and the antiderivative of 0 is going to be a constant. Okay. So y to the times e to the x squared is going to be equal to a constant, and isolating what we have here, we're going to end up with the general solution whereupon we're going to have y is equal to c times e to the negative x squared, and that will be the resulting solution for y. Again, so we have c times e to the negative x squared. Okay, and let me pause right here. And what I mean by the intermediate steps above, and just kind of a reminder. So again, the two terms we had here, I said, was a product rule expansion of taking the derivative in the independent variable of the product of the integrating factor times the dependent variable. So let me just give you a refresher. So you have d over dx of e to the x squared times y, and we have with the product rule expansion case, you have e to the x squared times d over dx of y, and we have also in the mix, you have y times the derivative in x of e to the x squared. And once again, for what we have in expanding, okay, so you have e to the x squared dy over dx. If you notice the case, you have y, and for e to the x squared, okay, so we're going to have in the mix, okay, so you're going to have y times e to the x squared, and again, you have times the derivative of x squared, and for this portion, this will go to 2x. And if you already see that the derivative of e to the x squared goes to 2x, e to the x squared, that's quite all right. So we have in the terms, okay, we have e to the x squared dy over dx plus, and we have 2x times e to the x squared times y. And if you notice, those are the exact same terms that we had in the preceding step before we rewrote in terms of compact notation or compressed notation. All right, now, and let's say that if we have as another case, let's say that we have dy over dx plus y is equal to e to the x. And if you notice, okay, for your p of x, okay, now we're going to have implicitly that p of x is equal to 1. So for the integrating factor. So again, we have e to the integral p of x dx, and that's equal to e to the integral of 1 dx. And so that is going to be e to the x. And if I multiply this equation by e to the x, so we have e to the x dy over dx, and I have plus e to the x times y. Again, I have times, or multiplying together, I have e to the x times e to the x. And once again, for what I have on the left-hand side, okay, again, that is going to be the product rule expansion of what I have for multiplying the integrating factor and the dependent variable. Okay, so I'm looking at d over dx of e to the x times y. And for what I have over to the right, e to the x times e to the x, you have e to the x plus x, so that will be e raised to the 2x. And integrating over both sides with respect to x, so I have e to the xy is equal to the integral of e to the 2x dx. Again, for the integral of e to the 2x, now if I took the derivative, I would be looking at multiplying by 2 from the derivative of 2x, but in the case of the antiderivative, I'm dividing by 2. So the antiderivative, and we have that 1/2 of e to the 2x followed by the constant. And for what we have in the case of the general solution, we have upon dividing by e to the x, I'm going to end up with 1/2 of e to the positive x. Again, since e to the 2x divided by e to the x is e to the x, and dividing by e to the x in the case of the constant is going to be the same as multiplying by e to the negative x. So we have for that solution of y, we have 1/2 of e to the x plus c times e to the negative x.